Yeah, comes on everyone. So last thing we have seen this, that surface tension force is S into L. S is a constant and L is a length in contact. Great. So let's see a few more examples. Suppose, let's say, if you have a surface, so think of like this, if you put something inside a cloth or something, uh, so the force will be acting somewhat like this, perpendicular to this line and parallel to the surface. And if you can visualize, it kind of looks like, if you can see my screen, it kind of looks like this. You're getting it? So if this is the cloth and there's a marker like this, normally it should be straight, but when you put a weight, what will happen? The surface will bend like this, right? Are you able to see this thing? So this is what I was saying. So the force will be acting. So how will the force act? So if you take this cloth and when it is bending, right, the forces, if you observe, they are along the cloth. The cloth is pulling it along this thing. So if you look at the same thing in the side view, this is how it kind of would look like. The forces would be like this. So this is F, this is F, this would be some theta, this would be some theta, and this would be your mg. So the 2f cos theta is balancing the mg. And here F is nothing but S into L, where L is the length of the rod. Similarly, if you take a soap film, remember last time we discussed a soap film will have two surfaces, an upper surface and a lower surface. So we have an upper surface here, we have a lower surface here. So basically, this is the soap film here. So we will have a force S into L and we'll have a force S into L. Getting it? Again, something similar like this. Again, if you look at the screen again, this is how it would look. So if you look at this thing here, now in the front view, it looks like only one surface, right? But if you look at the side view, can you see the two surfaces are pulling this up? So there is this one surface and there is this one surface. There are two surfaces actually. So whenever you take a soap film, right, that is what is happening. So when you're pulling the soap film, you're actually pulling two surfaces, the upper one and the lower one. Is that clear, everyone? So be careful. So whenever there's a soap surface, you have to take two times. So there is a force due to an upper surface and a lower surface. So if you have a rod like this, and if you have a soap film as here, this is length here. And if you keep a block of mass M here, then if you try to draw the FPD of this rod, you will observe there is one force here, S into L, and there's one force here, S into L. This is the back surface. This is the front surface. And these two are balancing mg. This is that SpongeBob music wala video. So that rod which is there, there are two surfaces there. So both are pulling the rod. Is this making sense, everyone? Have a look at this. A few examples. How do we calculate the force? Clear? Let's see a few more examples. Suppose if you take a plate, disk on a liquid surface. You can even try this with your finger. Okay, if you put a finger on the water surface and if you try to pull it up, did you ever observe the water actually slightly raises? Meaning, don't pull too much. If you just slightly try to pull it, you will observe you will get a surface like this. The disk, the water rate kind of sticks to it. This is how it becomes. Imagine your shirt ka button. If you pull your shirt ka button, how does the shirt come up? Like a small tent, right? So something similar. So when you create a disk or surface on a water, and if you slightly pull it, there's a slight increase. It's not too much, maybe like 0.1 mm or something, but you will see the water level actually slightly rises there. So if you see the forces acting on this, so there is a surface tension force here, which is 2 pi r into s, the disk own weight mg. So this was our main question: how much force is required to pull the disk out of the plate, the from the liquid surface? So other than the weight, you also have to give the surface tension force. So the force required is mg plus 2 pi rs. So the liquid rises a bit. Same thing. Suppose if I take a shape like this, suppose if you take a disk with a cavity, this is R1, this is R2. Now if you try to pull this up, this is how the liquid surface will rise. Is that making sense? So basically, wherever there is an edge or something, the water sticks and the whole thing rises there. Now, if you want to remove this thing, there's one force on the inside, surface tension force, which is 2 pi R1 S, and there is one more surface tension force on the outside, which is 2 pi R2 into S, and you also have your own weight mg. So in this case, the weight will be mg plus 2 pi R1S plus 2 pi R2S. This is a mains of bits level questions. Directly, they did ask a question like this. How much force is required to remove a disk on a surface when you just slightly pull it out? And surface tension is S and radius is R. So other than this, if you look at the surface tension values, if you increase the temperature, what will happen to the surface tension? Increase or decrease? With increase in temperature, surface tension, what do you think will happen? Think, I'll give you 10 seconds. And I want a reason also. Don't give me your feelings though. Temperature increases. We're talking about liquid na, right? We're not talking about the length. S का के value क्या होगा? We're not about surface tension decreases. Why? Think about it. Yeah, the molecules will start vibrating more rapidly. If the molecules vibrate more rapidly, then the interaction between the molecules will decrease, isn't it? So it's like the front line of calm people who are waiting for you to stop you. The front line who are pissed off, angry people who are confused and distracted. Right? Definitely the calm people will exert more force on you. So when the molecules on the surface are vibrating more rapidly with increase in temperature, right, the molecular interactions decrease. So molecular vibrations increase. which leads to decrease in interactions. So actually the bonds become weaker. So surface tension drops. And if you increase the temperature at boiling point, now at boiling point, the liquid starts becoming into a vapor. So the whole definition of surface goes off. The surface tension tends to zero. It becomes zero. At boiling point, this is also called as critical temperature. Next thing, if you add detergent into water, soap or anything, surface tension decreases. Again, same reason. This detergent will go and sit beside the water molecules. Now, in water molecules, there is a hydrogen bonding. So water has a stronger interaction than water detergent. So it's like you have a line of bouncers who are pretty strong. Now you remove some bouncers and put first standard kids there. What will happen to the line? It becomes pretty weak, something of that sort. So by adding detergent, surface tension of water decreases. Similarly, there are other types of liquids. When you add, suppose if you have a liquid like where water versus that liquid is stronger. So certain solvents will actually surface tension, but now this becomes case to case. So fundamentally, you should know whether the interactions are stronger or weaker. It is difficult to figure out. So hot water has less surface tension. So when you use hot water to take bath or wash clothes, right, the dirt gets removed more easily. That is the reason in washing machines you have an option of hot water. Ever seen it? I thought never used it, but there is always that option. Basically, force of water molecule is greater than force water detergent. So you are replacing weaker molecules with a stronger one with a weaker one. So interaction decreases. There are few theoretical questions. They'll ask you statement questions like this, so you should know. Have a look at this. So there, for if you see mathematically, we have only one formula that I taught you so far. F is S integral. That's it. And that everything else is the same. Next thing. Let's see a question. Previous slide. Which slide you want? What happened? Clear? Arush? Yeah. Let's see a question. We have a V-shaped frame. Angle is theta. We have a massless movable rod. You attached a block M here. Here we have a soap film. Surface tension is S. This slanting length is L. Gravity is also there. So this is the front view. System is in equilibrium. First question. Find M if the system is at rest. Second thing, if the block is pulled down by X, so it is at rest. So now you caught this block and you pull down by X, and then you released it. Find the acceleration of the block. And if you pull it down, the length will increase. There's more upward force than downward force, so the block will accelerate. Find the acceleration of the block. Let's get this. Mm-hmm. So the whole game is about to find the length. There's nothing there. Yeah, Nansh, you guys are forgetting something. There are two surfaces. Let's see the first one. So if you drop a perpendicular, if this angle is theta by 2, this angle is theta by 2. If this length is L, so this will be L sine theta by 2. And this also will be L sine theta by 2. So on the rod, we'll have force S into 2L sine theta by 2 into 2 by two surfaces. So I'll keep writing this for a few questions. And there is an mg. So balance them, 4SL sine theta by 2 is equal to mg. I have seen most of your seniors messing up like this. That 4 ka answers will always mess up. Answers will be like 10, 20, 1, 1, 2. So the 2 ka factor always messes up. So be careful with that. The 4SL sine theta by 2 is mg.
But could you just explain why did you take two surfaces? Because the surface in contact is only the massless rod, right?
What were you doing till now, God? ये example में क्या किया था तूने? Why didn't you ask me that this question here? Why didn't you ask me this question when I was showing you this example?
But ये तो 3D में है ना?
What you're talking? So you have a soap film. How many surfaces will be there? There is a surface on the front. There is a surface on the back. The picture would look like this,
Okay, sir,
God.
got it.
ऐसा होगा. It will be like this. Side view, if you see it in my screen, front ऐसा दिखेगा ना. Side view look like this.
Okay, sir, got
There
it.
is one surface on the front and one on the back. Meaning when it sticks also ना, देखो side view if you see ना, this is the thing. ये पूरा जो है ना, this is the soap solution ना.
Yeah.
So it is sticking ना here.
Okay, sir, got it.
Understood. It's like a rubber sheet which is stretching there. तो ये surface था और ये एक surface था. Don't forget, it will always be into 2. It was the same thing ना रे. यहाँ पे देखो ना, सिर्फ ये rectangle को मैंने V shape किया. You didn't get a doubt here. This you are convinced. Question is still not over. What is the acceleration if I pull this by x and release it? X is tan theta by 2. Okay. Mass नहीं है ये पूरा. You got an acceleration without mass. Okay. Maybe it got cancelled. So what will happen for the second part? So this was the initial position of the rod. Now the rod is pulled till here. Now see, this was the distance x. This angle is theta by 2. So that means because you pulled the rod down, you got an extra length, x tan theta by 2. Similarly here, this extra length is x tan theta by 2. And initially this length was 2l sine theta by 2. Are you getting this? By pulling the rod by x down, you have increased the length of the rod by 2x tan theta by 2. So now the force will be 2 into s, length will be, so if you just draw the FBD, this will be s into 2l sine theta by 2 plus 2x tan theta by 2 into 2, because there are two surfaces and mg. Now there will be an acceleration in the upward direction. So we get 2 4SL sine theta by 2 plus 4SX tan theta by 2 is equal to minus mg is equal to mass into acceleration. But I know this and this are equal. So you can actually simply, make a statement like this, that the 2L sine theta by 2 is balancing mg. The reason you're going up is because of this extra length, isn't it? When you pull the rod by x down, you created an extra length 2x tan theta by 2, and that is responsible for the acceleration. You could have just made an argument and finished it off. So therefore, we'll get acceleration is equal to 4s by m tan theta by 2 into x there. So m ka value, if you want, you can substitute here and you can get an answer. But there. Is this clear, everyone? So when you pull the rod by x downward, you have increased the length of the rod. So the surface tension force becomes more than the weight. So the rod accelerates up into 2 because two surfaces. Is this clear, everyone? Any doubts on this? Next one. We have a semicircular frame. So we have a soap film inside. Surface tension is. See, the moment I say soap film, there are two surfaces. So now how will the soap film apply forces? It will apply always perpendicular to the surface, perpendicular to the rod like this. So the forces will be like this. All of them will not be in the same direction. And let this radius be r. Find the force on the semicircular frame due to the soap film. So you cannot directly say S into pi r. Force is a vector quantity. Since all are in different directions, you have to add them vectorially. Find the force on the semicircular wire due to soap film. The previous case, you didn't have a problem because it was a line, all are in same direction. You could do directly S into L. I hope everyone is clear with that part, right? You can't directly say force is S into pi r. How do we do this? think it's a good one. It's a good question. This thing, what I'm teaching you now, this will come in at least 6 chapters. You've already seen this once before. You think for a minute, then I'll show you. There are 2 ways you can do this. Yeah, and करो ना integrate करके final answer बताओ. That only you have to do. What you said is right. Let's see. SR pi नहीं आएगा रे. Pi आएगा कहाँ से? You messed up the integration then. You are that hero in a Hindi serial. The heroine is in the front, he misses her, and then he goes to the airport and breaks the security and goes inside. And the security people shoot him down. So that's what actually would happen in real life. Movies में hero है ना, so we can't shoot him and kill him. Nikhil, you got it, Nikhil. Let's see. Now, first thing, now this integration I'm teaching you, listen carefully, important, because exactly same thing you will again notice in gravitation, electrostatics, magnetism. It comes 3 more times. This integration will come 3 more times. So whenever you see an arc, we have done this already before in center of mass. How do you choose an element? At an angle theta, take a small piece d theta. So this piece is so small, I can treat it like a straight line r d theta. So this piece will have a force like this df, which is 2 into s into r d theta. Why 2? 2 surfaces. This angle is theta. So if someone asks you what is the force on the small piece, the force on the small piece df bar is 2 s r d theta. You can't integrate this. The vector form is minus cos theta I cap minus sine theta j cap. This is the vector form. Is this making sense? When you integrate a vector, you always have to divide in terms of I cap, j cap, and then you start integrating. Again, meaning you go back to the fundamentals. What is integration? Summation, isn't it? Suppose if I have 3 apples and 4 oranges, you have 2 apples and 1 orange. If I add both of them, how many fruits do I have? How do you add them? Do you say 3 plus 4, 7, 2 plus 1, 3, so I have 10? That gives you no information, right? You add the apples, you add the oranges, and then you give me like 5 apples plus 5 oranges, whatever. So you add them vectorially. So you integrate this thing. So force on the semicircle is integral df bar, which will be 2 SR is constant. I'll put the minus n also outside. Integral cos theta d theta I cap plus sine theta d theta j cap. The limits will go from 0 to pi. So here theta starts at 0 and here theta ends at pi. Now, you know, integrate this thing, cos theta d theta integral is sine theta, sine pi 0, 0. So that will be 0 there. So this will be 0 I cap. And this guy will be minus 2 j cap. Minus 2 नहीं plus आएगा. Plus 2 j cap. So this will be 2 into S into 4SR minus j cap. So there's a way to write this. You can write this as 2 into S into 2R minus j cap. So if you notice this is actually the projected length. याद है fluid mechanics में I taught you projected area. So similarly, I can use something called a projected length. So the whole question, the answer looks like as if you can just join the ends of this thing to R and find the force on this length. Getting it? So there is a concept called projected length. Just like area, we have projected length also. That gives you answers without integration. Let me show you that more. But let me prove that why projected length works here. Kritik, adjust your camera a bit, can't see you. Is this clear, everyone? The integration part is clear. How did I choose an element? Why did I take a force? Why did I divide I cap, j cap? And then you have to integrate. This is how you integrate a vector. If you integrate a scalar, you don't need to do all this. Now, alternate. Suppose if you have a curve like this, let's say this is A and this is B, and let's say there's a soap film inside. Now at every instant, if you look at the force here, let's say this is DL1 bar, this is DL2 bar. So I can divide this entire curve into small vectors. This is DLN bar. Now the force on this each piece will be like this, perpendicular to this line DF1, DF2, DF, 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 so on, like this. So if you take the force on any random curve, that will be 2 into, because two surfaces, S into magnitude dl1 plus dl2 plus so on dln bar. But we know from the polygon law of vectors, if you have vectors like this, right? If you have vectors from A like this so on, the resultant vector is from the remaining tail to the remaining head, isn't it? This will be the resultant. We studied this in vectors. If n vectors are joined head to tail, the resultant vector is from the remaining tail to the remaining head. This is the polygon law. So for all these vectors, if you try to join them from here to here, the resultant vector becomes AB bar. This would be your projected length. So this can be written as 2 into S into magnitude of AP bar. So I don't care about the shape of the curve. I just join the ends of the line, make it into a straight rod, and then finish it off. So projected length can be defined like this: a line joining the ends of an open curve. So in case of projected area, if you remember, the area which makes it into a closed surface. You can argue like that also. If this had been a closed surface, net force has to be 0. The force on the line and the curve must be equal. A line joining the ends of an open curve. The only problem, this works only when surface tension is constant. Generally, S is constant for a given material, so that is not a problem. But if they do mess up, then integration is the only way. Suppose for some reason the S changes with theta or something, then you have to integrate. Then there's no way. This is the second time you're hearing this projected concept. First time is in fluid mechanics, projected area. This is projected length. You will again encounter this thing in electrostatics, magnetism, EMI, and modern physics. 6 times this will come. Any doubts on this? So if I take a few more examples, So if you have a semicircle, this is the projected length. The force will be two surfaces into S into 2R. You can have any type of surface. You can make anything. There. So for this is the projector length. So if you make a soap film here, the force will be 2 into S into length of A to B. It doesn't matter what kind of surface you take. So JEE mein they asked a question like this. This was A, this was B, this was C, this was D, this was C, this was B, and this was D. Inside we have a soap film. This is the opponent. The question was find the force on this frame. This was a question. What is the answer? Like I said, I really don't care about the shape. You just look at the opponents. This is the opponent, which is A minus 2C is the projected length. That's it. The most people started calculating on each section and they try to find. So force on the frame will be 2 into S into A minus 2C. Make sense? You can see and tell the answer. So projected length saves you a lot of time. At a level of mains and bits, you will be able to get pretty questions like this. You get decent questions. Saves you a lot of time. You can finish off this in like 10 seconds. If you can finish off like even 3-4 questions in 10 seconds, that will save you a lot of time. Even if you say 4 to 5 minutes in a JEE exam, that will be quite useful. And if the papers come like the way they're coming from the last 5 years in physics, you should be able to score at least 90 out of 100. If you don't score 90 or 90 out of 100 in physics, your percentile will go for a toss. Because this year, I think people who scored 80, unka physics ka percentile was like 98, 98.5. What is the meaning of that? There are more than 20,000 people who scored more than 80 marks. Paper is easy. People do score. Max may this time what? If you scored around 40, 45, you're getting 99 percentile. Last year in one particular paper, if you score 90 marks, you're getting 99 percentile. So physics in that way is quite scoring. At a mains level, physics paper is easy. It is scoring as long as you need to know all the concepts and everything. Are itna kyun? This year, my medical students, right? 2 people scored 90 marks plus. Medical students. Matlab, you think about it. Last year, my medical student is the highest. Because unka max nahi hai na. So 1.5 hours they wrote physics only. The point is this, meaning the level of the paper is such that even a NEET people can write. But then again, I trained them to a higher level. So, but still, clear with this. So these are the things which saves you a lot of time. And if you can save time here, then you can use the time in max. Next thing. You have a soap film. Like I keep saying, without chemistry, if you don't do your chemistry, you won't even enter top 5,000 ranks, advanced way. If you do physics and chemistry, you will go till 2000. What decides your rank after that is max. First, you need to score in physics and chem. Unfortunately, most people get obsessed with that. And they get max में 10 marks more, but they lose physics में 50 marks. Game over. Because your final rank is based on total score. No one really cares how much you scored in each subject. So balance your subjects for now. So we have a soap film and someone kept a loop of thread. Remember the last time I showed you the video? It becomes a circle. In this video. याद आया? So if you look at the soap film, the loop here, there is a force acting inside, there is a force acting outside. There's a force inside, outside, inside, outside. So the loop will take some random shape. Now what you did, you broke the inner soap film. And we observe it becomes a circular shape. So we get a circle like this, whose radius is r. And remember, the soap film is outside. So the surface tension is only pulling outside now. So if you're pulling outside with all directions, there'll be tension in the rope. Find the tension in the thread. So if you have a rope and if you're pulling in all directions with equal force, there'll be a tension. We have done this before. Anyone remember where? Anyone remember where we have done this before? This, if you take a ring and rotate with omega, there's a centrifugal force. The centrifugal force is pulling the ring away in all directions, because of which the ring will be under tension. Remember this video, the disc shattering wala? And we have done like this. So what changes in this question? What changes is this will remain same, this will remain same. Now here, in place of centrifugal force, you'll get 2 into S into R d theta na surface tension. Isn't it? In place of centrifugal force, now you have a surface tension force. Everything else is same. This is what I keep saying. You don't learn new things. There is already something there. You just need to relate it. Now try. I'll give 2 minutes. This will come 6 times. This is the second time you're already seeing it. Let's see. First, let's see the standard one. There are 2 ways you can do this. So you will take a very small slice, d theta. So I'll exaggerate this thing. So if I Make the figure bigger. Remember this thing, quite useful. You will see this thing again and again. 4 more times you will see this method. So tension will be T here. This angle also will be d theta by 2. This will be tension. This is also d theta by 2. So if you look at the components, the vertical components will be T sine d theta by 2. Also d theta by 2. And this will be 2 into S into, even though I drew it big, you must understand r d theta is very small. It's like a line. 2s r d theta. So balance the forces, 2 times sine d theta by 2 is equal to 2s r d theta. For small angle, sine theta becomes theta. So this will become 2t d theta by 2. 2sr d theta. So we get tension will be 2sr. Now there's a much faster way to do this using projected length. So alternate, draw FBD of a half ring. Don't draw the full or don't draw the part, draw for half. Now when you draw for the half, the advantage is the tensions will be in the same direction. So tension, tension. And remember the soap film is outside. So the forces are pulling in this direction. Now you can use projected length on this. So this force will be 2 into S into 2R, projected length. There you get it in one step. So 2 times tension is equal to 4SR. But for this, you need to know the projected length concept. The total force on the curve is this. Why did it take semicircle? Why didn't it take any other part? If I take any other part, problem क्या होगा पता है? Tension will be like this, na? I need to find the components again and do that. But in a semicircle, both the tensions will be exactly parallel. So they will directly add up. It becomes more convenient. Have a look at this. So this is how you can do this in the exam much faster using projected length. So you need to know the concept. Clear? Next one. Next one. So if you have a force, you also have energy. The next thing is surface energy. So let's say we have a frame like this. So consider a movable rod. Let this length be L and let there be a soap film here. So now what you do, apply an external force and slowly drag the rod. Now remember, the surface is trying to compress slowly by X. So you need to actually apply a force. So there is a force here, 2 into SL. So this force F will be 2SL. So this much force you need to apply to pull this thing. After some time, when you pull it by X, the rod must have come somewhere till here. The soap film is also increased. Now let's try to see this quantitatively, qualitatively what it is happening. Do you remember the story in the beginning when we started? We said the molecules on the surface have a net downward force, right? And the inside molecules have a net force zero. So these people are a little chilled out. So they're kind of an equilibrium. They have less energy, whereas the molecules on the surface have more energy. Think about it. In a concert, the person in the front line, if he's not shouting and just standing there, it looks very weird, right? So they have supposed to have more energy. Whereas once you are in the crowd, you are a little more silent and chilled out. Getting it? So the molecules on the surface have more energy compared to the molecules inside. Now, what you did here, when you pulled the surface, you have taken the molecules from inside and brought them to the surface. These are all the new molecules who came to the surface, isn't it? That means indirectly it didn't increase the energy of the system. And that is the reason you needed to do the work. So whenever you try to increase the surface area, you're bringing more molecules from inside who are actually stable to an unstable state. They're actually increasing the system of the energy. So that is the reason you need to do work in order to stretch a surface. Vice versa, the other way around. Since every system tries to achieve a state of least energy, right, the surface will try to compress in order to get a least surface area. That is the reason you can see if I leave this rod, the rod will just go to the left. So here, what is the work done by external force? The work done by external force is F into displacement. But you also know work done by external force is change in potential energy plus change in kinetic energy. Kinetic energy is zero since it moves slowly. That means whatever work you did, everything went into energy stored. So the change in potential energy, this will be 2 into S into Lx. So there's a better way of writing this. Change in surface energy is surface tension into change in surface area. So remember, for a soap film, there are two areas, front and back. So all the energy that goes will be used to increase the surface area. So the energy stored on the surface. There, that's your result, everyone. This is the second formula. Have a look at this. Is this clear, everyone? Does that logic making sense? The molecules on the surface have more energy, right? So you have to give more energy and vice versa. So a system will always try to attain a state of least energy, isn't it? Think of like this. Let's say we all are thrown into a room where the temperature is minus 20. It's very cold. What do you think we will do? We will all huddle up, right? Now, when we all huddle up, now you tell me, where do you want to be in that group? You want to be inside or you want to be on the outer side? You want to be inside, isn't it? Because it is more warm inside. Getting it? So now you tell me, so if you have a lot of molecules and no one wants to be on the surface because there's an unbalanced force, if everyone is trying to go inside, eventually what is the shape that you will form? A sphere, isn't it? Making sense? That means if you take liquid and put it in a gravity-free space, the shape you get is a spherical. Now think about it. Why are planets round? Did you ever see a planet in cube shape or rectangle shape or any other weird shape? Given enough time, right, any planet, right, will eventually become a spherical thing. Maybe because of rotation there'll be a bulge, but a sphere has a least energy in terms of gravitation. Radial forces, that is also a reason, but in terms of energy, you can argue like that. So if you take liquid's gravity-free space, so there are two ways you can argue. Everyone is trying to push inside, and if everyone is with equal force, you'll get a very symmetrical shape, and that's a sphere. So the molecules on the surface have a net inward force. Everyone is trying to push inside. And this also creates another thing. If everyone is trying to push inside, the pressure inside becomes more. That leads to an excess pressure in a liquid drop. We will see that in the next part. So molecules on the surface have net force. Towards the liquid. for behaving as a film and having more energy, why are you relating these two? What is the relation? You tell me.
So like if they have more energy, they should be like moving around more.
Now, again, what kind of energy is this? So when you say energy, there's only kinetic energy. There's no other type of energy. What is the whole story we said? Surface tension is what type of energy? Potential, bonding energy, or kinetic energy?
Bonding.
It is the molecular interactions, right? It is not kinetic energy. When you say more energy, always don't think kinetic. No, it's like a people who are standing in line who are catching their hands
Yes, sir. So like
that way
because it requires more energy, it doesn't want to
to
increase its
break
own
those
area.
things. Something like that.
Yes, sir. Thanks.
It forms a sphere. Getting it? So that is one argument you can give. Another way to argue this thing is molecules on the surface. In Antarctica, when the winter approaches, temperature drops to -35, -30, -35. So all the female penguins, right, they leave the male penguins with an egg and they go for hunting. Maybe they go on a vacation or something. Right. So only the male penguins are left over with an egg. If you have seen the movie Happy Feet movie, Happy Feet, did you see that? That's a penguin animated movie. So when you have that penguin, right, and I'm not drawing it properly, but if this is a penguin, they keep the egg here between the legs, so shielded by all that fur and everything. That's the reason penguins walk like that weird thing. Getting it? So egg is there, between the legs, and they stay there at a temperature of -30 degrees for months. Now, what people observed, if it's only one penguin, right, it will die. These penguins do something weird. They all start forming a group huddle. You'll form, huge, like hundreds of penguins forming a group. And what they do, the penguins which are there, right? This penguin stays outside for some time, then it goes inside, this comes out, this goes out, this comes in, this goes out, this comes in. So they keep on going like a conveyor belt, like a cycle. The penguins are exchanging places continuously in and out, so that for some time you're warm, you can conserve your energy, then some other guy will take your place, and so on. Like this, they'll survive for months. Right? And what they found out, right? Because again, all penguins are not equally strong, so you won't get a perfect sphere, but yeah, you get closer to a spherical shape. If every penguin had equal strength and everyone is equally strong, you would have got a perfect circle. So that way. So molecules on surface possess more energy than molecules inside. Due to the unbalanced forces. So, and we know to minimize the energy, I want less molecules on the surface. That means I want less surface area. To minimize the energy, the system will try to have a minimum surface area. Now comes max. So for a given volume, which shape will have the minimum surface area? Meaning if I give you 1 kg of some material, and if I tell you to make any shape, you'll observe for a sphere as a least surface area. This comes from max. So for a given volume, sphere has a least surface area. That means if you take an ice cube in a gravity-free space and if you let it melt, what will happen to all the water that that forms? It becomes a sphere. So ice cube will become a spherical water drop. So you can explain a lot of things: the water in a gravity-free space, the shape of the planets. The spherical, the sphere shape is a very special in that it has the least energy. So that is the reason, right? If you see planets also, you'll not find, this, okay, small asteroids and all are okay. But if the planet size becomes pretty huge, the spherical is the best shape that you get. So it would kind of look like this. International Space Station ISS. There you can see that the water is wobbling a bit, but it is close to a sphere. There. Now, if you put a red and blue, you get a green color. This is the International Space Station. You can see a proper sphere it is. Now, he's putting an antacid tablet there. So, normally, when you take an antacid tablet, right, you get carbon dioxide, you burp, isn't it? So, what does the gas do? It goes up. Again, what is up and down? Opposite to gravity, isn't it? So, now you tell me in a gravity free space, what is up and what is down? There is no up and there is no down. So, how does this gas should go? We just leave it for some time. So for gas, every direction is up and every direction is down. So there is no concept of up and down here. There, it forms something like this. Can you see? It looks like some chemistry ka molecule, na? So basically the gas bubbles are forming, in all directions there. This is how the shape would have looked. There, so if you throw water in a gravity-free space, that's what will happen. You get a bubble. Raindrops are close to spherical, same reason. Because of gravity, they do get distorted a bit. Clear, everyone? There. That is a catch. So there, this is the numerical there. So change in surface energy, that's into change in surface area. All clear with this? Let's see a question. So we have a big spherical drop. Remember, this is a liquid drop. Radius is r. Surface tension is s. So this is broken into n identical drops. Find the change in surface energy. This is a standard thing. Came multiple times in mains. Get this. So when you break a big drop into small drops, you change the surface area. And this is the formula. So change in surface energy, surface tension into change in surface area. So you just need to get the area, more of a geometry problem. Get it? You got a minute. रूट नहीं आएगा गॉड. What kind of numbers you got, right? 4 pi r square. रूट नहीं है behind. That is wrong. नहीं आरुष, that is also wrong. 30 seconds more. Right Puroja, but final minus initial करना पड़ेगा. Let's see. So what remains constant? The volume, isn't it? So this will be 4 by 3 pi r cube will be n times 4 by 3 pi small r cube. So small r will be r by n to the power of 1 by 3. So change in surface area will be n times 4 pi r square. There are n bubbles minus 4 pi r square. This will be n 4 pi r square by n power 2 by 3. So this is 4 pi r square n to the power of 1 by 3 minus 1. Therefore, change in surface energy is S into delta A. 4 pi r square S into n to the power of 1 by 3 minus 1. Check. Clear everyone? So if you take 1000 drops, that would have been 10 power 3. So you'll get 10 minus 1. So did you notice one thing? So when you break a big drop into small drops, you increase the surface area. And if you increase the surface area, you increase the energy. So where are you getting this energy from? Where are you getting this energy from? One, when you're spraying the water, you have to give some energy, but some of the energy is actually absorbed from the atmosphere. So that is the reason. Did you ever see this thing? When they spray water on you, it feels a little cool. You see that water ke liye, plants ke liye, we take their water and we spray, na? You get into a fine mist. So it actually cools down the surrounding a bit. So if you ever seen an air cooler, not AC, not air conditioning, air cooler kabhi dekha? It looks like this. You have a box. They sprinkle water here. There's a grass kind of thing here. And the water is sprinkled. And we have a big fan here, which is rotating. Ever seen this thing, air cooler? So this thing, right? Normally what happens, right? If you go to a place like Nagpur or something, where during summers, right, it gets really hot, more than heat, right? The problem is there is no humidity. The air becomes very dry. And when you switch on AC, AC also removes the humidity. So you have a problem. ACs don't work that well. So what this thing does, right? When the water falls on this grass, the surface tension is breaking, the area is increasing. So the inside temperature drops a bit and you're blowing this cool air. The one, it provides moisture. Second, it provides a little cooler air. Not much. Maybe outside temperature is 50. This thing will make at least 44 degrees. So it will feel a little better. So it gives you the temperature difference. Did you notice this thing? If you have a lot of trees in a surrounding area, their temperature goes down. Similar reason. When there is something called transpiration. Ever heard about it? Biology. Mein. So under the leaves, you have a fine pores where the water comes out like a thin mist. So when you have a lot of tree cover, the surrounding area temperature drops a bit. Again, one other reason. The water is converted into fine droplets. So my campus now, IIT Mein, Madras, if you see, during summers, outside temperatures used to touch 44, 45. But inside the campus, right, temperature used to be around 38, 39. We used to have that 4, 5 degrees difference. You will see this even in IIT Bombay also. Once you enter the campus, it feels little, better than on the road. Right. So because of the tree cover and all, one of the reason why it feels little cool. Another is anyway, it blocks the radiation. So that is another thing. So there. So when you break a droplet into a fine droplets, the surrounding temperature drops. Next thing, you have a soap bubble. surface tension is radius r. Outside the pressure is P naught. What you did, you took a straw and you started blowing air inside it. So when you started blowing air inside, this guy became a bigger soap bubble. Like this of radius 2r. You get in the question? You took a soap bubble, you kept a straw and you blowed air and you made a bigger soap bubble. So the soap bubble is blown from r to 2r radius. Find the work done by external force. So how much work did you do in order to do this? It didn't pop, so don't worry about that. There are two things happening here. When you're blowing the bubble, you're increasing the surface area, but you're also fighting the atmosphere, isn't it? When you're trying to expand, aren't you pushing the atmosphere also outside? So there are two things happening here. Most people forget that atmosphere part. So work done by external force is used to change in surface energy. Plus work against atmosphere. So you increase the surface area and you also push the atmosphere. So this is S into delta A plus this is pressure P naught into delta V. It's a constant pressure, right? Since the pressure is constant, we can, it's a constant pressure you're pushing. So it's a pressure into delta V. You're done. So surface tension area will be 4 pi. Final minus initial 2r whole square minus 4 pi r square. P naught into 4 by 3 pi 2r whole cube. 4 by 3 pi r cube. Simplify this. Remember, there's only one surface, huh? So into 2 nahi karenge. This is a liquid drop. So into 2 won't come. Be careful with that. How much is this? That is 4, 4, 16 minus 4, 12. S pi r square. That is 28 by 3 P naught pi r cube. Check. That's your answer. Is this clear, everyone? Clear? There, that's a thing. Isn't inner surface exposed to? God, what are you? Nee, wait, sorry, the soap bubble, na? It's not liquid drop. My mistake. It's 2i, because there are two surfaces. My mistake. I got confused with the previous question. Yeah, you're right. This guy's actually 24. You have to take into there's an inner surface and outer surface. It's a soap bubble. Clear with this? Next thing, like I said, if every molecule is trying to push inside, then there will be a pressure inside. Excess pressure inside a soap bubble and a liquid drop. Let's do a liquid drop first. Consider a liquid drop of radius r. Surface tension S. Now draw the FBD of half the drop. So when you draw FBD of half the drop, what are the forces acting on this? One from inside. We have pressure inside into pi r square. And from outside, the atmosphere is pushing you in all directions like this. We can use projected area. This will be P naught into pi r square. And if you look at the surface tension, where will the surface tension act? It will act on this surface here, on the circumference like this. Which is S into length, which is 2 pi r. Able to visualize how is that surface? Imagine a coconut. For example, if you look at my screen, if this is like a coconut, if I try to break it like this, how is the force acting on this? Isn't it acting on this circumference? So Chona, if you have a coconut like this and if I try to pull it like this, how is the force acting? Isn't it just acting on the surface? Making it, remember, the surface is acting like a membrane. So when you're trying to pull this, only this surface is trying to prevent you from coming out. So the surface tension, again, remember surface tension, it's a liquid drop, तो अंदर कुछ surface नहीं है. Or even you can imagine like this. It's like if you take a balloon and if you just draw an FBD here of this half piece, this right side balloon is stretching the left balloon like this, isn't it? Along the circumference. The forces will act on the surface. So if you try to balance these forces, because the liquid drop is in equilibrium, P in into pi r square will be P naught into pi r square plus S into 2 pi r. So from here we get pressure inside will be pressure outside plus 2s by r. So the excess pressure delta P is P in minus P naught is 2s by r. So the surface tension will increase the pressure inside by a factor of 2s by r for every one surface. This is a proof by force method. There's also another way called energy method that they'll ask you in HSC. Find the excess pressure in a liquid drop using force method, using pressure method. So there is something of that sort. Clear with this? Now, if I just try to put down these results, but have a look at the derivation, ask me if you're still confused with the direction of the forces. surface tension will act only on the surface. So surface tension won't act inside. It is acting only on the outer layer. So if you take a liquid drop, so if the outside pressure is P outside, this is P inside. But again, when you say inside and outside, exactly how do you know whether it is inside and outside? It's a bubble, though you know. I'll give a simple logic. Say, think of it like this. Let's say if you have a membrane here, if this is P1 and this is P2, if P1 is greater than P2, surface kya hoga? If P1 is more than P2, what will happen? It will become like this, na? So inside is always the concave side. So P concave minus P convex. If you have more pressure, you'll push it. So this becomes the inside. This becomes the outside. So that is how you can figure out what is in and what is out. Because higher pressure will push the surface, that will be concave. This is 2s by r. Delta P. But if you take a soap bubble, remember soap bubble has two surfaces. If here the pressure is P naught, here the pressure will be P naught plus 2s by r inside the soap solution. Here the pressure will be P naught plus 4s by r. So for every surface, will increase the pressure by 2s by r. So P inside minus P naught will be 4s by r. There, have a look at this. So a liquid drop has only one surface, whereas a soap film has two surfaces, so the pressure doubles. Clear with this? So we'll see some problems on this. Take a break, come back by 7:05. Any doubts so far? Anything you can ask? Or else take a break, come back in 10 minutes. We'll see. We'll be doing that later on. But cylindrical surface भी वही करेंगे ना. उसमें that is actually easy. So you'll have a surface like this. So this will be what? S into L. This will be S into L. Projected length कितना होगा? P in into L into H. This will be P naught into L into H.
Sir,
Where H will be 2R, isn't it? करके देखो आएगा. There you will get something like S by R आएगा. We will do. करने वाले बाद में. First I wanted to show the regular shape and then we'll see. हाँ अंश.
sir, in the previous page,
Hmm.
you have taken the projected area of the concave surface because वो components कट जाएगा.
नहीं मतलब इसका बोल रहे हो?
हाँ
या उसका प्रोजेक्ट एरिया ले सकता ना. प्रेशर इज कांस्टेंट एवरीवेयर हियर.
हाँ ओके ठीक.
इसके लिए तो नहीं है ना. इसके तो डायरेक्टली एरिया तो ऑलरेडी फ्लैट है.
हाँ
That way. So pressure or force on a curved surface is P naught into projected area if pressure is constant. Clear? Chalo, come back with 7:05 then. So let's see one more question. Let's say we have 3 concentric soap bubbles. S is the surface tension. Let this be radius r. Let this be radius 2r. Let this be radius 3r. Outside the pressure is P naught. Let this point be 1. Let this point be 2. Point be 3. Find the pressure at 1, 2, 3. Let's get this. I want 1, 2, 3, all 3. This was easy. Now, like I said, what is 1 for surface 1 who is outside? P naught. So P1 minus P naught is 4s by radius. What is the radius? 3r, na? So P1 is P naught plus 4s by 3r. P2 minus P1 is 4s by 2r. So P2 will be P naught plus 4s by 3r plus 4s by 2r. P3 minus P2 will be 4s by r. P naught plus 4s by 3r. 4s by 2r plus 4s by r. Make sense? You just keep adding for every surface and you're done. Easy. Next one. Any doubts on this thing? Arush, clear with this? Ahana, Devansh, Pratik, Kritik. Clear. Next thing, a simpler one. We have a small bubble and we have a big bubble. This is R2. This is R1. And let's say R2 is greater than R1. And let's say both are connected with a pipe. So the question is, how does the air flow? In which direction does the air flow? Small to big or big to small? It's an easy one. This was a PYQ. Think, I'll give another 10-20 seconds. Now see, if you take the pressure here as P1, here the pressure is P2, P1 is P0 plus 4S by R1, P2 is P0 plus 4S by R2. You will notice here, if radius is more, pressure is less. So the smaller bubble whose radius is less, pressure is more. So smaller bubbles have higher pressure than bigger bubbles. And we know air flows from higher pressure to lower pressure. Therefore, P1 is greater than P2. So smaller bubble becomes smaller, bigger bubble becomes bigger. Is that clear, everyone? So eventually this bubble will vanish and it will become like a soap solution here. It will form a soap, a small drop. It will become soap solution. There will be no air bubble left on the left-hand side. So it would look kind of like this. Look at this thing. So how to make giant bubbles. So normally if you just use a regular detergent, right, it doesn't work that well. Glycerin, that is the catch. The glycerin will make a soap film much thicker and they're more stable. And this is that, washing machine ka pipe hota hai na? So you cut it in half. So you join this, you get a circle, make a ring. So now you pour soap solution in this. So that ring acts like a thing there. You can get a film. Yeah, you need that thing. So that you can create big soap films like this. Look at this thing. This is from actually electrostatics. So if you rub a rod, the rod becomes charged. You will see this later on. This is induction. So bubble gets attracted. It's a concentric soap bubbles. Now, if you keep more and more, actually the pressure inside increases like really to a high value. At some point, they can't withstand. This is what would happen. This is a good one. Huh? Look at this thing, what he's doing. If you observe here, there's a bigger ring and there's a smaller ring. So when you blow air through this, you're actually creating two soap bubbles, isn't it? The small ring is creating one bubble and the bigger ring is creating one more bubble. So there are two bubbles actually. Now he's filling this with a, so there are actually two bubbles inside. If you can see, there's a shade. He's filling this with a, flammable gas like hydrogen or something. You can't see the gas. So he's using some smoke, to get a visualization of the gas. So that you can visualize there's a gas inside. Now, if you blow the inside bubble out, there. So we have a bubble with gas inside. Now see what he's doing. He's making a hole in the thin ring. But tell me one thing, what will happen? The pressure inside is P0 plus 4S by R. Outside is P0. Agreed? Pressure inside is more than outside. So the moment you make a small hole in that central ring, the gas will leak out. Now, as the gas leaks out, bubble becomes smaller. If the bubble becomes smaller, pressure will increase more. So the gas will come out even faster. So as the bubble becomes smaller and smaller, the gas is coming out faster and faster. So if you put a fire on the top, what will I see with the fire? Initially, you'll see a small flame, then the flame will become bigger and bigger, isn't it? Is that making sense? So smaller the bubble, higher the pressure, bigger the flame. There, see. So the air is coming out initially. You can see it forms a tornado there. And observe the size of the flame. Huh? Can you see how it became? You can see that in a slow motion. See? The flame is just burning more vigorously. The gas is coming out faster. So there we clear like smaller bubbles have higher pressure. So this guy creates a lot of stuff. I'll post this, you can check it out. This is that thread wala thing. Circle thing there. He made it with 4 straws actually, the square frame. You can do something. Did you see that ring? Remember I gave an example. If you have a disc and if you're pulling, the surface pulls you down. It kind of looks like this. If you try to pull the disc out, you can see the soap film, how it is dragging the whole ring down. It's like the button ka thing, yeah. There. So film comes back. There you can see more bigger ring. This is a good one. You get a cubical bubble. So this is what happens if you put bubble on that's a dry ice. Carbon dioxide is heavier than air, so the bubble floats. This is also easy to try. Put a dry ice in the water and put soap solution. You get foam. For Diwali time here, that black color thing, when you put fire, you get a thing. That's all dry ice. So yeah, you can check it out. I'll post this thing. You can see for more there, but you got the main crux of it. The smaller the bubble, higher the pressure. Clear with this? Now let's see something better. So we have a soap bubble, radius r. S is the surface tension. Outside pressure is P naught. So inside it is filled with air whose viscosity is eta. So it's a viscous air. Now what you did, you connected this to a pipe whose radius is small a, length is L. Now we know the pressure inside is more than outside. So what will happen? The air will start leaking out. So air will start leaking out. So air leaks through the spin thin pipe. So find the radius of the bubble after time t. At t0, the radius is capital R. So if the air is continuously going out, the bubble eventually will become smaller and smaller. So what is the radius after time t? Let's get this. This would be a good one. Think for a minute, then I'll give you an idea. Now, when you see this question, right? Meaning, how do you even start? Like, actually, I know radius and something. Question is understood, but what is the first thought process that you get? So when I see this question, see what I think. So I'll see this thing and think like, okay, surface tension, fair enough. You talked about viscosity of air. Okay. And then you're also talking about a pipe is connected. So this is how I will think. Okay, in viscosity, we had only three formulas. One is Newton's law of viscosity, eta A dV by dz. Fine, that is for sheets and stuff. Another one was Poiseuille's equation. That is for actually pipes. Fair enough. That looks like relatable. The third was Stokes' law. That is for spherical bodies. So that is gone. So you're saying indirectly there is a pipe here and there is a viscosity here. There's a length here. So this thing kind of looks like Poiseuille's equation. What is Poiseuille's equation? Delta P pi r power 4 weight. Delta P is what? Pressure difference between inside and outside. But where does that come from? That comes from surface tension, excess pressure, isn't it? You're getting? So that means I know, okay, so surface tension excess pressure is actually making the air flow from inside to outside. So I have to use a Poiseuille's equation there. You're getting it? Now, I don't know whether this will come or not, but this is my starting point. Now I'll start solving the problem. I will start with the Poiseuille's equation, and then I'll try to see what can I get from there. Now try. This is what should go through your head when you're looking at a question. You're getting it, like, you think, right, how do I even know how to start? This is how you start. You have to see and you have to get clues. You talked about viscosity. In whole of viscosity, there's only 3 formulas. The Newton's law of viscosity, eta I dv by dz, is for sheets. Stokes' law is for spherical bodies. The only thing left is Poiseuille's equation, that is for pipes. So when I think about Poiseuille's equation, there's a delta P ka term, and there's a pressure difference between inside and outside that comes from surface tension, excess pressure. Now everything looks like it is making sense. So one thing I'm clear, I have to integrate. So when you have to integrate, how do you start? After time t, let the radius be x. Are you getting this? Now, these things, what I told you, these things you will not find in books. You're getting it? This thing, the thought process that I'm giving you, right? This is what you will learn when you do a lot of practice. When you solve enough problems, after every problem, you need to ask yourself, what made me think like this? And when you can tell like this step by step, means you actually understood. Exam it, then you will get speed. When you see a question, your brain knows how to figure out how to start. But if you're just randomly solving, getting the answer, but if you're not doing this exercise, what I did right now, you will not remember, like, your brain will have a hard time figuring it out. Then maybe you need to practice 4 to 5 times more in order to get that feeling instinct, natural wise. But if you do this after every question, I think for every chapter, even if you do 70, 80 questions, you'll be able to figure out how to start a question. Anyways, give it a try. You got the idea there. Think I'll give you another 1 to 2 minutes. मेरे अंश 1/4 आएगा. You goofed up. Delta P is difference in pressure. So after time t, let the radius be x. Outside pressure is P naught. Inside pressure is P naught plus 4s by x. So what is the excess pressure? 4s by x. You kept a pipe here, length L, radius A. So from Poiseuille's equation, d volume by dt is pi delta P r power 4 by 8 eta L. Now what is volume here? At any instant, the volume is 4 by 3 pi x cube. So d volume will be 4 by 3 pi 3x square dx, which is 4 pi x square dx. Minus sign because x is decreasing. So this is minus 4 pi x square dx by dt. This is pi delta P is 4s by x. You're getting, I don't want pressure inside. I want pressure inside minus pressure outside, the difference in pressure across the pipe. So here the pressure was P naught plus 4s by x. And here the pressure was P naught. The difference I want. And then this is a power 4, radius is a, by 8 eta L. So once you got till here, it is done. 4 pi gets cancelled, x will go this side. Minus x cube dx. 4 pi is gone. So S a power 4 by 8 eta L dt. Limits when time is 0, radius was capital R, this was x, and this was t. This would be x power 4 minus r power 4 by 4. Minus n goes that side, Sa power 4 time by 8 eta L. We get x is equal to r power 4 plus s minus Sa power 4 time by 2 eta L whole to the power of 1 by 4. Check. This is a problem based on surface tension and viscosity. This is how they'll ask in advance. I can even ask you, find the time when the bubble vanishes. So put x is equal to 0. You'll get the time when the bubble goes away. So you'll get a finite time. Is this clear, everyone? That was the main thing there. So as the bubble becomes smaller and smaller, the pressure becomes more, the air flows out faster and faster. Any doubts on what we did? So the main thing is that you have to write a Poiseuille's equation. That was the main thing to figure out. And the delta P comes from excess pressure. That's it. Once you figure it out, then it is just math. Clear, Ansh? Got the mistake? Any doubts on this? Kritik? Ojas? Clear? Devika? Purvaja? Parth? Clear with this? Next one. Can I go ahead? Any doubts on this? Adi? Arush, adjust your camera a bit. Can't see you. Next one. Let's say we have a soap bubble. We have another soap bubble. These two soap bubbles combine to form a bigger soap bubble. There is no information about the radius. Nothing is given. That's not P naught. Two soap bubbles combine to form a bigger bubble. Delta A is change in surface area. So when these bubbles combine, the surface area final minus initial area is delta A. Delta V is change in volume. Find the relation between delta A and delta V. Answer should come in terms of S, P naught, delta A, and delta V. Assume isothermal conditions. Isothermal matlab temperature remains constant. Think for a minute. Let's see. So what did you get an idea here? When I see this question, the first thing that hits me is that assume isothermal conditions. When in a chapter like surface tension, why the hell are you talking about temperature? That is one. Second thing, when you combine these two bubbles, what remains constant? Don't tell me surface tension, I'll punch you. Don't tell me temperature, that is already given. Say something more sensible. अब भी बोला रे, surface tension will remain constant. That is not. Why will volume remain constant? Gases का volume can change when there's a change in pressure or temperature. Total energy of the system, no. Assume isothermal, meaning heat can go in and out. Temperature remains constant. Number of moles will remain constant. For a liquids and solids, volume remains constant. For a gas, number of moles remain constant. Isn't it? If you take a container of 1 liter and take that gas and put it in 10-liter container, volume becomes 10 liter, but the number of moles will remain same. That is a thing. You're getting it? Delta U is 0. That is useless. That is internal energy. What about surface energy then? When you say total energy, there's the surface energy also included in this. Kritik, I think you need to change your background, meaning you need to get a plain background or something. So do change that. It's pretty distracting and I can't see you. Half the time your face just vanishes in that thing. So I think the AI is the Zoom is not able to figure out whether it is you or that anime character behind you. Make it a white background next time. Or just blur the background. So make the number of moles as constant. So how do we start that? Start like this. Let this be R1. Let this be R2. Let this be some R. Pressure is P1. Pressure is P2. Number of moles is N1. Number of moles is N2. Number of moles is N1 plus N2. Ideal gas equation. Solve. I'll give you a minute. So you can assume R1, R2, R3, but make sure final answer should not have R1, R2, R3. So this bubble, they both combine. And you get a bigger bubble. So let this be R1, let this be R2, let this be R. So here this pressure will be P naught plus 4S by R1. This will be P naught plus 4S by R2. This will be P naught plus 4S by R. We are using the ideal gas equation, PV is equal to nRT. So if the number of moles is N1 here and the number of moles is N2 here, then the number of moles is N1 plus N2. So P final, V final will be N1 plus N2 RT. But N1 RT will be P1 V1, N2 RT will be P2 V2. Is that making sense? So P final V final is P1 V1 plus V2 V2. What is P final? P naught plus 4S by R. What is the final volume? 4 by 3 pi R cube. P1 is P naught plus 4S by R1. 4 by 3 pi R1 cube. This is P naught plus 4S by R2. That is 4 by 3 pi R2 cube. So shift all the terms to the left hand side. You'll notice P1 4 by 3 pi R cube minus 4 by 3 pi R1 cube. There is a change in volume. plus this will be 4s by 3r, 4 pi r square, 4 pi r1 square, 4 pi r2 square is 0. So this will be P naught into change in volume plus 4s by 3r into change in r nahi aayega na, r will cancel, is 0. There, this is the relation, everyone. So 3 P naught delta V plus 4s delta A is equal to 0. So if you look at this ratio of delta V by delta A, which is like 4s by 3p naught, will always remain constant, independent of the size of the bubbles. You mix any two bubbles, the ratio will always remain constant. The exam, you'll get 4 options like this: 3p naught delta V, 4s delta A, 4p naught delta V, 3s delta A. So they will mix and match the numbers. Is this clear, everyone? There. This is how it can be framed. Thermodynamics and surface tension. So the biggest hint, right, if you ask me, was that word assume isothermal conditions. The moment you hear the word isothermal conditions, you know the PV is constant. He's talking about that thing. That should give an idea about ideal gas equation use karna hai. And then when you think about a gas, remember for liquids and solids, if you remember this question here, liquid drop wala, this question, see, when the liquid drop was breaking, volume remains constant because it's a liquid. But you can't do that for gases. Because if you take a 1 liter gas, 1 mole gas, and put it in 1 liter, if you put 1 mole gas in 100 liters, it will occupy all the volume of the room, isn't it? So gas has no specific volume. It will just occupy the volume of the container. So volume of a gas doesn't make sense. Moles is a better one. Is this clear, everyone? Next one. Any doubts on this? Anyone not clear with anything? Arnav, clear with this? Arya, Adi, Arush, clear? Ishana, clear? Vignajit, Soham. Next one. We have two soap bubbles. Of radius R1 and R2 coalesce. So this is the word they will use. Coalesce karke. What it means is they're stuck to each other. Meaning it would look something like this. I'm pretty sure you must have seen bubbles like this. Ever seen like this? When you're blowing bubbles, sometimes 2-3 bubbles stick and go like this. So they're stuck like this. So we have a bubble here and we have a bubble here. It's like this. So this is your interface. So this bubble ka radius is R1. This bubble ka radius is R2. So this interface, if you extend it, that would form another bubble of radius R. And at this junction where the 3 bubbles are meeting, the angles will be alpha, beta, and gamma. So find the radius of the interface. So when the 2 bubbles stick, it will form a surface interface. So that is also spherical. So find the radius of the interface and find alpha, beta, gamma. So alpha, beta, gamma are the angles at the point where the 3 surfaces interact. How do you do this? This is also another standard question. You should definitely remember the results. Get the radius na Vihan. You just typed something and you're just staring for me to say, okay, waste of time. Focus on the question, get the rest. Examiner, who will tell you you are right? Go ahead. See, how do you even start this? This is a little different, but not difficult. Now, when you just look at the interface, if this was P1 and if this was P2, right? Remember the formula? P concave minus P convex? So for this thing, the excess pressure is 4s by r. So what is P concave? P1. P convex is P2, it's 4s by r. But what is P1 and P2? So for this radius R1, so P1 is nothing but P0 plus 4s by R1. So that is also a spherical bubble. So for this radius R2, that is also another spherical bubble, P0 plus 4s by R2. So P0, P0 will cancel. You end up with 1 by R. It's a standard result. Remember this. Mains or bits is a direct question in the exam. So R will be R2, R1 by, you can take a modulus R2 minus R1. The minus sign simply indicates the surface is in the other side. So concave or convex. So this is the result. Now suppose if R1 becomes equal to R2, then you get the interface R tends to infinity. Means what? What is R tends to infinity mean? It's a circle with infinite radius. Straight line. So the surface interface becomes like this. We have two bubbles of equal pressure. It will become a line like this. So a straight line is a circle with infinite radius, which will turn at infinity. That is the meaning of this. It becomes a line. Clear? Keep that in mind. This is the first part. That's a standard result you need to remember. Exam like mains or bits, directly they'll ask you. They'll give you the numbers, they'll ask you. What about the angles? Now look at this. If you just draw the FBD of this section here, I'm going to exaggerate this. This is how it will look. This is the soap film. This is the soap solution. So if you choose a point here, you'll observe the soap solution from this side is pushing with pressure P. This side is pushing with pressure P. This side is also pushing with pressure P. Why should the pressure be same? Ask yourself, if the pressure is not same, then the soap solution will go from high pressure to low pressure. Isn't it? So the soap solution will keep moving till the pressure becomes same. So pressure at that point must be same in all directions. Pressure is same on all three sides. If the pressure is not equal, the soap solution will move till the pressures become same. because the bubble ka surface is in equilibrium. So the pressures have to be equal. If they're not equal, soap solution. So great. So we accepted the fact that the pressure is equal. Now the second part comes here. Now you tell me, if three equal forces are acting at a point, and if the body is in equilibrium, then what is the angle between them? If three equal forces act at a point, and if the body is in equilibrium, it forms an equilateral triangle. And what is the angle between the vectors? 120, na? You have to put head to head or tail to tail. Therefore, alpha is beta is equal to gamma is equal to 120 degrees, independent of radius. You take any radius, you do anything you want, these angles won't change. That's the best part about this question. It's a good result. So you will get this angle 120, this angle 120, and this angle 120. There. So these are two good results. Direct questions in the exam. Have a look at this. Is that making sense, everyone? Three equal forces acting at a point, and if they're in equilibrium, you have to have 120. There's no other choice. That's the best part. So exam, what they'll do now, they will say two bubbles of radius r and 2r coalesce. Find the angles. People will think you have to use r and 2r. You don't need. You'll always get 120. Clear with this? So if you see, all these are spherical surfaces and all, but sometimes you also see, other kind of surfaces like cylindrical and all. So let's see a more general thing. Excess pressure across a surface. So this is a more general result. Let's say if you have a surface like this, the radius of curvature is r1. You're getting it? You can have two different surfaces, two different radius of curvatures. This is r1. This is r2. You're getting it? So there are two different radius of curvatures there. Now on this, if you take a small strip, this side is concave, the outside is convex. Now for this small strip, if you try to draw the FBD, are you able to visualize how can I get two surfaces like this? Meaning if you take a paper like this, look at my screen. If I take a paper like this, can you see this is one radius of curvature? Now if I turn it like this, can you see this is another radius of curvature? So there are two radius of curvatures, right? So for this paper, when I bend it in some awkward way like this, right, it can have one curvature this way and one curvature this way. Do you remember this one? I showed you this here. This one, the Pringles. This can have two radius of curvatures. This is one R1. This is R2. Making sense? The Pringles will have two different radius of curvatures. So now if you take this surface here, or the small strip, I'm exaggerating the figure. And if you try to write the forces, so we will have, this is the tension forces which are pulling it. Like this. The other side, the forces are pulling it like this. let's take this angle to be d theta 1, and let's take this angle to be d theta 1. Derivation is not important. This is d theta 2. So this length will be r2 d theta 2. This length will be r1 d theta 1. So if you look at the side view, this is that circle cutting which we did today. Let me write the red one. So side view, if you look at the red one, the forces, right, are the black ones. The tension is T2. Tension is T2. So the T2 is pulling it. If you take the black one, the tension is pulling it. And this angle is d theta 1. So this angle is d theta 1 by 2. So the vertical components will be T2 sine d theta 1 by 2. This will be T2 sine d theta 1 by 2. Right? And what is T2? So here this will be T2, which is surface tension S into length, which is R2 d theta 2. This surface tension will be T1, where T1 is surface tension into R1 d theta 1. Surface tension forces surface tension into length. So far the diagram is clear, everyone. So basically you're treating this as one circle. This is one circle. I am trying to apply this one, everyone. In case you're wondering, I am trying to do this in two directions. Right? And if I look at the other side view, like really don't worry too much about the proof, but just try to understand how are the steps coming. So the other side view, you will see the black one. Now who is pulling it? The red forces, which is T1 and T1. This angle will be d theta 2. Is that making sense? Look at this. The black one, who is pulling? The red ones are pulling it, na? Tangentially. And the red one, the black ones are pulling it tangentially. Is that making sense? Then if you take the components, same story. This will be T1 sine d theta 2 by 2. This will be sine d theta 2 by 2. Then, now, if I draw the whole thing again, look at this. So we have two components here. This entire thing is pulling down with 2 T1 sine d theta 2 by 2. Similarly, this is also pulling with 2 T1 sine d theta 2 by 2. I think I wrote reverse. The black one should be that. 2 T2 sine d theta 1 by 2. 2 T2 sine d theta 1 by 2. The black one is pulled by the red guys. 2 T1 sine d theta 2 by 2. And who is balancing this? The pressure difference. So the excess pressure difference P concave minus P convex into area. So area of this strip will be length into breadth, which is R1 d theta 1, because it's a small rectangle, R2 d theta 2 will be this total forces, which is 4T1 sine d theta 2 by 2 plus 4T2 sine d theta 1 by 2. And we know T1 is surface tension into R1 d theta 1. T2 is surface tension R2 d theta 2 by 2. Perfect. So we get P concave. नहीं wait, 4 नहीं आएगा. नहीं, 4 नहीं आएगा. I did a mistake. This whole thing, right, is this and this, the black ones. So this is 2 only. So P concave minus P convex into this guy will be R1, R2, d theta 1, d theta 2. This will be 2. For small angles, it will become d theta. So T1 will be S R1, d theta 1, d theta 2, plus SR2, d theta 1, d theta 2. D theta 1, d theta 2 cancels. We get P concave minus P convex. Send it that side. You will get S into 1 by R1 plus 1 by R2. There, it's okay if you don't remove the derivation, but this is a result for any surface where R1, R2 are two different radius of curvatures. This is for single surface. For a soap film, you'll have into 2. But you're getting what we did? This entire black one ka vertical component is this. This entire black ka vertical component is this. So there are 4 forces which are pulling down, and they're balancing the pressure difference between inside and outside. Should definitely check this out again. Decent proof. We are doing this in 2-dimensional, that circular thing. The result is important. So let me show you how this result works. Example, if you take a sphere. Now when you take a sphere, this is how you get the radius of curvatures. You draw 2 surfaces perpendicular to each other. This is also R, this is also R. So for a sphere, R1 is equal to R2 is equal to R. So the excess pressure delta P will be S into 1 by R plus 1 by R, 2S by R. That's the standard result. For soap bubble, it is 4S by R because there are 2 surfaces. Now, this is quite useful for other surfaces also. If you take a cylinder, can you tell me what are the 2 radius of curvatures for this? If you take a cylinder, this is one circle, radius R. Perpendicularly, there is no radius. This is another radius. This R tends to infinity. Is that making sense? For a cylindrical surface, one surface becomes a straight line and one surface becomes a thing. So here the delta P becomes S 1 by R plus 1 by infinity. So the excess pressure is S by R. So how does the surface look like? Example, if you take a glass plate, so if you take mercury plus glass, this is how the liquid will be. It will bulge like this. This is how the liquid would be. You're able to visualize how it is? It's like a cylinder. Think of like this. Take 2 bread slices, put a lot of jam and just press it. So it just may, the jam will come out like this, na? Can you visualize that? It's like an half cylinder. So here, if the pressure is P naught, here the pressure will be P naught plus S by R. Getting it? This will be 2R. But same thing, if you take 2 plates, water between glass plates. The surface would look like this. It will be inward like this. The water becomes like this. So here, if the pressure is P naught, so this is a concave side. And here, the pressure would be P naught minus S by R. Is this making sense, everyone? Are you able to visualize this picture, how it looks, the water between the plates? It's the surface now will look like this thing. See, I'll try to draw. Think of like this, huh? It's like this. Can you see that curve? It looks like this. It's a half cylinder. The liquid will be here inside. So here, this is one radius of curvature. The other radius of curvature is a straight line, infinity. Able to visualize now? So for a cylinder, one radius of curvature is infinity and another radius of curvature is r. Is this clear, everyone? So this formula is valid, right? The best thing is, even if you give me some random surface, I can figure it out and I can use this. Generally, they won't go beyond cylinders, but just in case. Clear with this? So that's a bit about excess pressure. So next class, when we catch up, we'll continue from here. We'll do maybe 1 or 2 more on this, and then we'll go for something called capillary. Next class, we'll wrap up this part. And then if time permits, maybe we'll do elasticity, a little introduction also. Like I said, it's a small chapter. Even elasticity is a small chapter. We should wrap up everything in another 2.5 classes. And then we'll start off with SHL. Okay, with that, we'll wrap up for the day. The exam is online till Saturday, so make sure to give it. So, and we have almost done 10 problems. So do make sure to go through the notes today. They're not tough, but if you don't see them today, you will forget in 1 or 2 days. Okay, with that, we'll wrap up for the day. I'll see you guys again on Tuesday at 5:30 as usual. So any doubts, anything, you can stay back or else you're free to leave. So take care, stay safe.